What is the nothing? Does it refer to an absence of space, time, matter, and energy, or does it entail a different state of existence beyond our current understanding? If the universe did generate from nothing, what physical process or mechanisms were involved in its emergence? Scientists explore these questions by delving into fundamental theories like quantum mechanics and exploring the behavior of particles at the smallest scales. They also investigate cosmological models such as inflation theory and the concept of multiverses to understand how the universe could have evolved from a primordial state. Furthermore, experiments and observations conducted with advanced telescopes, particle accelerators, and other cutting-edge technologies aid in testing hypotheses and gathering data to unravel the mysteries surrounding the origin of the universe from nothing. One theory proposes that the universe goes through cycles of expansion and contraction. After a period of expansion, the universe will eventually slow down and contract back to a singularity, leading to another Big Bang and the birth of a new universe. This process repeats infinitely, making the universe cyclical. Some theory propose that the universe emerged from a quantum fluctuation in a pre-existing state of nothingness. In this scenario, the laws of quantum mechanics play a pivotal role in generating the Big Bang. Physicist Brian Cox discussed that eventually the last star will cool and fade away, leaving the universe dark, lifeless, and devoid of meaning. Some theory propose that our Big Bang, the birth of our universe, might have originated from a previous state of emptiness, resembling the cold and dark future universe that awaits us. As for the second theory, it suggests that there was no singular event or first beings that sparked the universe's existence. Rather, the universe has always existed and will continue to do so perpetually. Theory 2, which suggests that there is no first man or woman or no singular event that sparked the universe into existence. Instead, the universe has always been and will always be in state of perpetual existence. While the third theory posits the existence of multiple universes, each governed by its distinct set of physical laws, constants, and conditions. According to this concept, our universe is just one member of an infinite assemble of parallel universes, where each universe within its vast array may exhibit diverse properties. This idea is known as the multiverse theory or many worlds hypothesis. It suggests that beyond our observable universe, there might be an unimaginably vast number of other universes, each with its own unique characteristics. These universes could have different fundamental forces, particle properties, or even dimensions, making the entire multiverse a complex tapestry of parallel realities. Another theory posits that the universe goes through an eternal cycle of creation, evolution, and destruction. According to this idea, our universe undergoes a repetitive pattern of Big Bang, followed by expansion, eventually leading to a contraction or a big crunch. During the contraction phase, the universe collapses in on itself until it reaches an extremely dense and hot state, triggering another Big Bang and initiating a new cycle. This process perpetuates indefinitely with no true beginning or end. The cyclic universe theory draws from concepts in cosmology and theoretical physics, attempting to address questions about the origin and ultimate fate of the cosmos without invoking a single unique event like the Big Bang. The Big Bang theory indeed provides valuable insights into the birth of our universe, but it leaves a significant gap when it comes to understanding what happened before this event. The conditions that led to the Big Bang, including how all matter, energy, space, and time were compressed into infinite density and temperature, remain mysteries. The concept of material or physical matter coming into existence is one of the central questions in cosmology. The answer lies in the early moments after the Big Bang, during what is called the Grand Unified Epoch. At this epoch, the universe was governed by high-energy forces that were unified. Electromagnetic, weak nuclear, and strong nuclear forces were combined into a single force. As the universe cooled and expanded, it underwent a process called a cosmic inflation, causing the Grand Unified Epoch symmetry to break, separating the forces we now observe in the universe today. During this phase, various particles were created, including quarks, leptons, and other fundamental particles, which eventually formed the building blocks of matter. The Triple C theory stands for the Conformal Cyclic Cosmology theory, and it was proposed by cosmologist Roger Penrose. It is an alternative cosmological model that suggests an eternal cyclic universe, challenging the traditional view of the Big Bang as a unique event marking the beginning of the cosmos. In conformal cyclic cosmology, the universe undergoes an infinite series of cycles, each comprising an aeon. During each aeon, the universe expands from a Big Bang event, goes through an extensive period of expansion, and eventually approaches a state of near infinite expansion. At this point, the universe enters a new aeon, starting again with a Big Bang. The interesting aspect of the Triple C theory is its treatment of the concept of time. Penrose proposes that as the universe expansion reaches its near infinite state, time effectively comes to a stop. In this state, the concept of time loses its traditional meaning, and instead a new time scale called conformal time becomes relevant. Conformal time allows the comparison of events at different points in the universe's history without the constraint of a linear time arrow. The theory suggests that during these cycles, any information from one aeon to the next is lost due to the vast expansion and apparent end of time. As a result, each aeon appears to have its distinct universe despite being casually connected to previous aeons. The idea of universe operating in two fundamental ways can be understood as follows. The dynamic aspect refers to the universe's continuous evolution and change over time. According to the Big Bang theory, the universe originated from an incredibly dense and hot state, and since then it has been expanding and evolving. Galaxies move away from each other. Stars form and die, and various cosmic structures come into being through gravitational interactions. This dynamic mode signifies the ongoing transformation and development of the universe. The probabilistic aspect relates to the behavior of fundamental particles and phenomena at the quantum level. Quantum mechanics, a fundamental theory in physics, describe the behavior of particles in a probabilistic manner, meaning that certain properties of particles such as their position and momentum cannot be precisely determined. Instead, they are described by probability distributions. This probabilistic nature is intrinsic to the fabric of reality at the smallest scale and has significant implications for understanding the origin of the universe. When contemplating the universe from nothing, both dynamic and probabilistic modes come into play. The dynamic aspect encompasses the vast scale of cosmic events, the evolution of galaxies, and the unfolding of the universe over billions of years. On the other hand, the probabilistic nature at the quantum level is relevant to the very beginning of the universe, particularly during the Planck epoch, which is an extremely early phase of the universe history when space and time were intertwined and quantum effects dominated. During this epoch, uncertainties and fluctuations in the quantum fields could have influenced the subsequent expansion and structure formation of the universe. To comprehend the universe from nothing, scientists endeavor to merge these two fundamental modes, exploring how quantum effects might have given rise to the dynamic evolution we observe today. This ongoing effort remains a fascinating and challenging area of research that seeks to understand the deep connections between the behavior of particles at the quantum level and the vast cosmic structures that define our universe. In conclusion, exploring the origin and nature of the universe from nothing presents profound questions that challenge our understanding of reality. The Big Bang theory offers remarkable insights into the birth of our universe, but the mystery of what occurred before it remains unsolved. The universe operates in two fundamental ways, dynamically with continuous evolution and change over time, and probabilistically with quantum uncertainties at the smallest scales. The concept of conformal cyclic cosmology proposes an eternal cyclic universe, but it remains a speculative hypothesis. While we have gained remarkable glimpses into the universe's beginnings, there are still many open questions. What happened before the Big Bang, and how could all matter, energy, space and time be packed into infinite density and temperature? The emergence of material and particles during the Grand Unified Epoch remains a subject of ongoing research. Additionally, the idea of the multiverse with countless parallel universes challenges our understanding of the cosmos. Scientists persist in their efforts to unravel these mysteries through the study of fundamental theories like quantum mechanics and cosmological models like inflation theory. Advanced technologies and observations aid in testing hypotheses and collecting data. However, there is much more to explore and get deeper insights into the birth of our universe and its underlying principles. As we delve into these questions, we continue to appreciate the vast complexities and wonders that define the cosmos.